Our last topic is LeChatlier's principle, which guides us in predicting the effect changing conditions will have on the position of equilibrium. LeChatlier's principle says that if a system at equilibrium is disturbed, the position of equilibrium will shift to minimize the disturbance. So, what would happen if we add or remove reactants? If we have equilibrium established and then we add a reactant, that means that we're going to increase our rate of the forward reaction, decrease the rate of the reverse reaction. Actually, it won't affect the rate of the reverse reaction, but it will increase the rate of the forward reaction. And it's not going to affect K at all, but the reaction will shift to form more products until we reestablish equilibrium. So, add reactant, we're going to shift towards the products to reestablish equilibrium. Basically, we're going to counteract whatever we did to the system. So here we can see that if we add some, in this case products, some nitrogen dioxide, we're going to disturb our equilibrium here, and we're going to shift to make more of the reactants in this case, and that will reestablish the equilibrium. Here's a picture for you. We have our original equilibrium. If we add some of a reactant, we're going to shift to get rid of that reactant, form more products, and then reestablish our equilibrium at new concentrations for both reactants and products. What if we change a volume? After we've established equilibrium, the container volume is decreased. So we have to think about different phases. For a solid, that's not going to affect anything. For a liquid, it's not going to affect anything. For a solution, if you're changing the volume, molarity has volume in it already, and so you're not going to change your overall concentration. But for gases, if you change your volume, you're going to change your pressure. So your value of K is not going to change, but if we're in the gas phase, it's going to, changing your volume can change your partial pressures, and you're going to shift to the way that has fewer gas molecules so you can reestablish equilibrium. So here's a picture for you. If we have nitrogen and hydrogen, we have 4 moles of gas on our reactant side, 2 moles of gas on our product side. So if we increase our pressure by lowering our volume, we're going to shift our equilibrium to the side that has fewer moles of gas to try to reestablish that equilibrium and counteract what we did. So if we increase our pressure, decrease our volume, we're going to shift towards our product side. If we decrease our pressure, increase our volume, we're going to shift towards the reactant side in this case. You always want to count the moles of gas on each side and then decide which way it's going to shift. What about temperature? You can think of exothermic reactions. They release energy, and you can write heat as a product for an exothermic reaction. Or in an endothermic reaction, they require heat to happen as a reactant, so you can write heat as your reactant, and that will help you use LeChatlier's principle to determine the effective temperature. So in this case, we have our reaction between N2O4 and NO2. This, written this way, it's an endothermic reaction. Heat we can think of as a reactant. And so if we get rid of heat, we're going to shift to make more heat. We're going to shift towards our products. So at a low temperature, we're going to shift this way to favor our reactants. So we're going to favor our reactants. If we heat it up, we want to get rid of that heat, so we're going to shift towards the product side, and so at a higher temperature, the NO2 is favored. There are some things that don't affect the position of equilibrium. Catalysts provide an alternate mechanism. They work equally on the forward and reverse reaction, and they're not going to affect the position of equilibrium. Let's work through thinking what's going to change in our reaction here if we do these different things. So our reaction 2 sulfur dioxide plus oxygen goes to 2 sulfur trioxide, has a delta H of negative 198 kilojoules at equilibrium. The negative 198 kilojoules means that this is an exothermic reaction, so we can think of heat as a product. How will each of the following changes affect the equilibrium concentrations of each gas once equilibrium is restored? So if we add more oxygen to our container, we're going to shift to get rid of the oxygen, so we're going to shift towards products. If we condense and remove our SO3, we're getting rid of a product, so we're going to shift to form more SO3 and again favor our products. If we compress the gases, on our reactant side, we have 2 plus 1 is 3 moles of gas. On our product side, we have 2. So compressing the gases, we're going to favor the side with fewer moles of gas, which again is the products. If we cool the container down, we're getting rid of heat. We would want to shift to try to make more heat. Heat is a product since it's an exothermic reaction. So again, products. If we double the volume, we're going to lower our pressure. If we lower our pressure, that's going to do the opposite of increasing the pressure, so we're going to favor our reactants. If we warm up our mixture, that's the opposite of cooling it, so again, favor our reactants. This one's always a little tricky. Adding the inert gas helium to the container. That's going to increase our overall pressure, but it is not going to change our partial pressures. Our partial pressures will stay the same because adding an inert gas, while it will increase the total pressure, it's not going to change the volume or the number of moles or any of that. And so adding an inert gas is going to do nothing. Just like adding a catalyst, like we talked to on the last slide, also does nothing. So there's the answers there.